All right. I'm happy to kick off this session of lightning talks. The purpose of this session is to give you all an opportunity to tell us about, or some of you, an opportunity to tell us about the work that you do or things that you're interested in, and to do so briefly so that we can hear from any of you. We have a great list here of people who we have 10 talks coming up here your way. So the rules are as follows. If you are, I'll call you one by one, and as when I call you, please join the Zoom, share your screen, and present from your own machine in that way. The Zoom is it's in the Slack general channel. It's the Elder Commons, also in which you can find in the shared info folder. Okay, and with that, I will. I'll post after I call on the first speaker here. I will post the list so that you know when yours is coming as well. Just a list of names and titles so you can see that full width. But with that, I will now call on Hallie to talk about test reliability of movie watching and resting state functional connectivity.
Do the test on here. Recording in progress. Okay. Thank you. Should I use computer audio or no? Okay.
Recording in progress.
Okay. There I am. And now we'll go present.
Yeah.
And here. Words. And share screen.
You're on.
Okay. And then we'll do this. Okay. Good. Okay. Okay. And this works? Yes. Okay. We're all set. Sorry. So I already showed you all what I do now the other day on Friday with the Brain Effects app. So I'm going to tell you a bit about what I used to do about movie fMRI as an acquisition state for functional connectivity-based precision psychiatry. So this project combined two different fields. The first one is precision psychiatry, which is this idea of using large amounts of data, in this case, functional connectivity, to tailor diagnosis and treatment to each individual patient. The idea is promising, but there's a few things that are holding the field back. We need the FC data to be more reliable, we need it to be more sensitive to individual differences, and we need better data quality and longer scans. So this is where the second field comes in of movie fMRI, which is the idea of showing people movies while they're in the scanner rather than resting state or task. And this offers some advantages in terms of the functional connectivity data. And luckily for us, that overlaps a lot with what we need for precision psychiatry. So, oops, got a little excited. So this led me to combine these two fields to see if movies actually can help specifically for precision psychiatry. To do that, I looked at 3 different brain regions that we know to be important for psychiatry, and in each one of them measured reliability in 4 different ways and compared that between movies and rest FC. With that, we found that in the DLPFC and the pre-SMA, 2 of our regions, movies and rest were equal in terms of their reliability, and then in the TPJ, temporoparietal junction, movies outperformed rest in terms of the reliability. More recently, I ran this analysis on all of the brain regions, including the subcortex to appease Alex, wherever she is. And you can see another shiny app there with those results. Overall, this finding suggests that movie fMRI offers region-specific advantages for FC-based precision psychiatry. And this is work from my previous lab in Vancouver with Tamara van der Waal. So thanks to the lab there.
Okay, great.
Give you that.
Moving right along, in the spirit of lightning talks, questions will be taken afterwards. Find the people and ask them then. Next up, we got Lupita, studying interactions between visual pathways and.
Sorry.
Yeah, when you join, don't join the audio. That way we won't get echoes. Studying interactions between visual pathways using single pulse electrical stimulation. Take it away, or come over here. Wonderful. Come present here.
Yeah.
For this, you.
Thank you.
David Owl.
Okay. Hi, I'm Lupita. I'm a postdoc in Mayo Clinic in multimodal neuroimaging lab with Dr. Dora Hermes, and I'm studying visual pathway interactions with single pulse electrical stimulation. So we stimulate a pair of electrodes with 6 milliamperes, and then during this stimulation, we are recording all the other electrodes in the brain, about 200 electrodes. And we made this procedure during 12 times. So we have 12 trials, and we apply this CRP method that Dr. Miller taught us in one of the conference. And then we have the duration of the response and many different measures from this method, including signal-to-noise ratio and others. And we can calculate the reliability of these responses. So, for example, we can see that ventral to lateral interactions are longer than ventral to early visual areas. So, here we can see the conversion and divergent paradigm for the different visual areas. We are working with posterior areas that are early visual areas from Benson Atlas, V1, V2, and V3. And for lateral and dorsal, we use one Atlas. And for ventral areas, Rosenke Atlas. And we are exploring how these areas interact. Here we have the coefficient of determination for check the reliability of these measures. And in general, we are looking how long are the response, how is the connectivity between these areas, and we are working on that. Thank you.
Great. Next up is Angelina, who will tell us about clinical phenotypes associated with cerebral small vessel disease, a study of 45,013 UK Biobank participants.
Sure, can you all hear me well?
Yeah.
Sure, I'm just gonna share my screen. Just bear with me, and then can you also confirm if you can see my screen now?
You can see your screen.
That's okay. So I took that seriously and I literally limited myself to a single slide, but hopefully that will be fun. Okay, so just to recap, I'm based in Scotland. I'm one of the people joining online, and I am based at the University of Glasgow. For those of you who have not been, you should definitely make sure you come visit. I'm a third-year PhD student on a doctoral training program in precision medicine. And when I'm not doing neuroscience stuff, you typically see me trail running, climbing mountains, or traveling. But that's enough about my personal side. When it comes to my work, I am a cerebral small vessel disease researcher. So small vessel disease is actually the most common vascular disorder of the brain, which might be a surprise to some of you. And when we think of small vessel disease, we typically associate it with a few features that we can see on magnetic resonance imaging. And here on this brain, you can appreciate some of the most commonly occurring features of small vessel disease. So we've got things like white matter hyperintensities, perivascular spaces, and microbleeds, and this can be both cortical or subcortical. So this is really enough about the neuroimaging hallmarks of small vessel disease. When it comes to the clinical manifestations of the condition, though, these are very complex. So small vessel disease leads to hemorrhagic and ischemic stroke, cognitive impairment and dementia, but also things like mood disorders, gait and mobility impairment, and even things like urinary incontinence. So the idea of my PhD project really is to shed light on the complicated ways in which small vessel disease can manifest. And I'm doing that using big data modeling. So when I talk about big data, one of the data sets that I have been using quite extensively has been the UK Biobank. Again, some of you might be familiar with it. That's one of the biggest biomedical databases in the world. It contains information on more than 500,000 participants from across the United Kingdom. And there's literally everything and anything you can think of. There's extensive imaging data, but also cognitive, cardiovascular, sensory, neurological disease condition information, and all that stuff, as well as genetic information. So what I do is I work in the framework of what we call a phenome-wide association study. So again, some of you might be familiar with GWAS. What I'm doing is actually the reverse of GWAS. So I'm doing PHEWAS, where I test for associations between presence of small vessel disease in the brain and a wide range of clinical phenotypes. And typically, the big merits of this approach is that it can help us shed novel associations, but also maybe refute some of the associations that have been previously established. And we can also identify novel associations between the phenomenon that we're interested in and all the data that we're modeling. This, of course, has a lot of implications, not just for research, but also for clinical practice, because it can help us understand how small vessel disease can affect patients' lives. And so far in my PhD, one of my biggest takeaways has been that small vessel disease really is not just in the brain. It's actually more diverse than previously thought, and it can manifest in multiple ways across the body. So really, one of the messages that I'm trying to drive with my PhD is that small vessel disease is a multi-system whole body disease. That's me. Thank you.
Great, thank you so much. Next is Victoria, who will tell us about multimodality approach to functional imaging. So maybe not. We will skip on to the next one, which is Dylan, who will tell us about discrimination, policy, gender nonconformity.
Thanks. Hey, so this is happening sort of in parallel to my neuro work, and I figured it'd be fun to share it here. I guess the problem that I work on in this space is gender nonconformity in the context of psychosis, where gender nonconformity is sort of the experience of gender that is not aligned with sex assigned at birth. And in the context of psychosis, it's especially hard to assess, because part of psychosis is like a poor sense of self, and also can include feelings of what's the word, disconnection from your body and feeling like your body isn't part of you. Okay, so in this data set, which is enriched for kids, young people at risk for psychosis, we're seeing this overrepresentation of gender nonconforming folks compared to the national average. And I think this type of data tend to be used by some sides. This is a highly sociopolitically charged topic right now. I think these type of data are used to kind of support the pathologization of gender nonconformity. So it's important to describe the mechanisms that sort of account for this increase in representation that we're seeing in people at risk for psychosis. So when you, in short, when you control for the discrimination that these gender nonconforming folks in this sample are experiencing, there is no relationship between gender nonconformity and psychosis symptoms, which is pretty powerful. There are some nuances that I'm not going to describe, but in general, you can think that if you got rid of the discrimination or lowered the discrimination in society against gender nonconforming folks, maybe you wouldn't see this overrepresentation in folks with at risk for psychosis. This is a slightly different study, totally different study, using the ABCD data set, which is this nationally representative sample across the United States. What we did was we separated the states into 3 categories. One category shown in pink have supportive trans policies across a 4-year period. The states shown in green show an increase in support over time. And then the states shown in blue show a consistently unsupportive political environment in those states. So then we looked at the rates of change in the PQB, which is a measure of psychotic-like experiences. And basically the trend here is that in all these groups of kids, so sorry, on the x-axis you have time, on the y-axis you have this measure of psychotic-like experiences. In the pink, you have kids who are in those low, no change states, those unsupportive states. In green, the increased states, and in black, the high support states. And as you can see, all of these groups are showing declines in psychotic-like experiences, except for the one group. I didn't define the groups. Pay attention to the bottom right corner and the top left corner. The top left corner being the conforming group, and the bottom right corner being the most non-conforming group. So what you're seeing is that there's one group that's showing an increase in psychotic-like experiences over time, and that is the gender nonconforming kids in states with unsupported policy. All in all, discrimination and policy play an important role in why we're seeing this overrepresentation in folks at risk for psychosis. Thanks.
Okay, next we'll hear from Alex about evaluating reliability in subcortical structures, which is the 7 Tesla. Share screen.
Thank you.
Okay, hi, I'm Alex. I truly do mean this when I say this. If you have any suggestions or feedback here, I would be so grateful. Our results are a little surprising in a good way, but we're still trying to brainstorm next steps in this week part of my dissertation. So it's all very exciting, but if you have any ideas or thoughts after, please chat with me. I really appreciate that. Okay, so when we're thinking about reliability, subcortical nodes are traditionally far less reliable than cortical nodes. And this is because of 2 reasons. The first is the size. Subcortical nodes are extremely small compared to the cortex, and also second, their location. So they're surrounded by cerebral spinal fluid and also other forms of non-neural artifacts. And we're missing. Oh, I guess I had a little. So in one of the subcortical structures that is particularly prone to both of these constraints is the periaqueductal gray. This is a region in the brainstem that is known for fight or flight in the animal models, and also in humans, modulation of pain, and also modulation of threat. So the PAG is 3 to 4 millimeters wide and 14 millimeters long, and it's also surrounded by the cerebral aqueduct. So those are 2 major constraints on the subcortical structure. And one of these ways to potentially address the constraints of low reliability in subcortical areas is to use masking strategies. So here we try to see the effect of subject-specific masks on this PAG and how that could affect reliability. So what we're looking at when we're looking at the group masks is that we looked at the functional connectivity between PAG and amygdala. Again, another very strong functional connection in the animal literature. In the very top, we have the hypercortical support atlas of the amygdala, and then we have the brainstem atlas, and then we have the Wagner atlas. And on the very bottom, we have the subject-specific PAGs, and the pink is the PAG, and the blue is the cerebral aqueduct. So you can see just how close of a proximity and perimeter they have to each other, truly. In order to look at this, we did resting state. There were 3 runs, so it's not a traditional task-free test reliability paradigm in the sense it's one session, but we were interested in looking at the differences or similarities across runs. We used 7 tests, and we had a total of 81 subjects. And interestingly, we found No. Not my audio.
Yeah, somebody else in
Okay.
the next.
Totally fine. Absolutely, no worries. Just gonna make sure that was me. What we found between PAG and amygdala functional connectivity is that it was actually very, very high. So what we're looking at now is the ICC, and that's a measure of task-free-test reliability. And on the side, you'll see that it ranges from from poor to fair to good. Those are 2 fours. It's supposed to be poor to fair to good to excellent. So just use that in your working memory. But these are values that we would typically see for the cortex and subcortex, so very interesting. The other interesting thing about this is that we didn't see a huge effect on masking strategy, which is very interesting considering the literature about subject-specific ROIs are supposed to really help enhance this reliability measure. So what we're planning on doing next is looking at the influence of local versus global CSF on reliability. So what we're doing is we're doing this for the whole subcortex, not just the PAG, and we're creating local CSF blasts for all of these ROIs, and then we're going to see the effect that they have local versus global regression on reliability. And so far, we've found some pretty interesting stuff that didn't fit on the slide, but I'll be able to talk about later. So yeah, that is my work. If you have any thoughts, please let me know. Thanks.
Thank you. Next, we'll have Gabby, who will tell us about probing the limbic network. You can put it up here.
Recording in progress.
Okay. No. There it is.
Do you have slides?
I do. And I need to share. Share. Right here. Yes, okay.
Okay.
So, hi, everyone. My name is Gabby, and for people that I haven't interacted with, I'm a first-year PhD student at the Mayo Clinic in the biomedical engineering and physiology track, and I work with Dr. Hermes in the multimodal neuroimaging lab. We're a small group that is based in Minnesota, and we're really part of a larger group on neuromodulation at the Mayo Clinic. We collaborate a lot with Dr. Royal, Dr. Inge, and Dr. Miller. And the goal, what we do the most is really to try to figure out how the brain is connected, which is not an easy task, right? So we're particularly interested in neuromodulation therapies, especially since we have several FDA-approved therapies and we have different outcomes. So really one of the lines that our lab focuses on is really trying to understand brain networks. And the one that I am interested in, that I have worked before and that I want to keep working on, is the limbic network. So the approach that we want to take to understand the limbic connectivity is really to not see the limbic system as a single network, but more like a diverse interconnected subnetworks. So what we want to do is not only try to modulate different gray matter regions, but really to understand how these gray matter regions are connected through different white matter regions and all that. So
the way we test for this is really combining two different measurements, one of them being structural MRI and the other one being intracranial EEG measurements after applying direct electrical stimulation. So I think what we pretty much do, patient gets into the clinic, we get diffusion MRI, then we estimate the white matter bundles, and later we stimulate different gray matter and white matter regions to see whether we can activate different subnetworks distinctively. So before, because at least we have like 3 main limbic subnetworks, so before we have proof that we have this bulk waveform after applying stimulation that seems to be very distinct to the posterior limbic network. So again, I'm more than happy to talk to you about like the different details and the data that we have. But as you can see here in this panel, like each of these different panels is a different connection, and we have like a wide variety of EEG waveforms after applying electrical stimulation. So what we really want to do is try to link these waveforms and to test whether these are particular to a different subnetwork. So again, before we prove that one of the waveforms, the half wave, is particular to a posterior limbic system, but now we want to prove like in different systems whether we have like another evoked response that is particular to that. And that being said, if you have any questions, please reach out.
Right, next we'll have Michelle, who is here to tell us that NEPOP is looking for contributors. That's the title of the talk. Guys doing? Share the screen.
Okay, so hi everyone. As part of my PhD, I'm a PhD student with GB Flynn. As part of my PhD, I'm working on this package, software package, and also just general framework called NIPOP. I won't go into too much detail because I have talked about it in one of the sessions already. But basically it's a framework where we think of it as a best practices protocol for how to reproducibly organize and process data from neuroimaging clinical studies, such that you know what you did and how you did it, and then you can keep track of who has been processed successfully, etc. I'm very happy to talk about it later if anyone is interested about learning more about it. But the point of this lightning talk is to say that we think of this. So currently it's more of it's pretty much within the lab. There are people who work on it. I'm the main person on it currently. But we're looking for contributors from the community and to start building a community basically. So then there's like examples. So this is the current team who like work on this with, more or less of their time. Yeah, you could be part of the team. If you are interested in contributing to like the open science ecosystem, we do very like when we work with tools that already exist in the ecosystem, like bids and like boutiques and things. There's a link to the GitHub if anyone is interested in looking into this more. But what I wanted to briefly show is that kind of like we talked about on Monday morning in the GitHub project management thing, we have basically a GitHub repository that's here with the README and then an issues page where there's a lot of issues, mostly that some of us have written when we found that things didn't work or that maybe it would be nice to have this extra feature. And in particular, there's a label called Good First Issue, which is something that GitHub has by default. So if like anyone is interested in contributing to other open source projects, this is something to look for. But Good First Issue is something that is would be nice to have. It's not necessarily very critical to the project, but would be a good entry point for contributing and starting to learn about the software. And GitHub is very open and there's like discussion-based things. So I would be very happy if someone's like, hey, I'm interested in the project, I'm interested in contributing, what would it take? And we're very, I think we're pretty friendly. So if you just say, oh, can I know more about what you're required to do this? And I'd be happy to kind of give guiding points. And then you can do the assignment thing, and then you make a fork, and it's all very exciting, and then a branch, and then the pull request, and then eventually you get reviewed and feedback, and then it gets merged. Yeah, so that's pretty much all I have to say. But please feel free to reach out. I don't on GitHub or on Slack or email. I don't think I have an email on the site, but yeah, that's it.
Okay, next up is Erin, who will tell us about normative modeling approach for effects of gestational age on brain development. All right. We can put it right here and then join Zoom. You're on Zoom.
I am on Zoom. How do I
Okay,
connect?
so share your screen.
Oh, yeah, right, I forgot.
No worries.
Great.
Okay, take it away.
Hello, everyone. I'm Eran. I'm an MD PhD candidate at University of Pennsylvania. I work with Aaron Alexander Block, and our lab is actually don't have an acknowledgement slide, forgot to put it here, but our lab is BGD lab and works on brain gene development stuff broadly. So I'll just present like my proposal, like it's a very, very short version of my proposal for my thesis. There's not a lot of results yet, but I think it's quite interesting. So first of all, there's this idea of growth charts. I think a lot of you might be familiar with these in terms of weight and height that's commonly used for children, tracking growth of children when they're growing up in pediatrics. And the benefit of these is that it gives you a sense of how children are expected to grow throughout their childhood and adolescence, but you can also place any individual child on a centile for their sex and age and get a sense of whether they are falling behind or whether they are following along with their peers. And then also longitudinally, you can see if someone is following their own centile, because for example, something that might happen is if a child is just shorter than average population, they're say on the 15th percentile, only taller than 15% of the top population. And then they continue on to 15th percentile, that might be okay, but another kid might be on the 70th percentile. And if they stop dropping percentiles as they get older, that means something might be wrong because they're not following what you expect them to follow. So it's a way of sort of having individualized understanding of where an individual falls, but also having a sense of how a population and in general growth happens. So our lab, along with a lot of collaborators, I think this paper has a lot of authors, harmonized a bunch of data, I think over 100,000 scans or something, but please don't quote me on the numbers. Across the lifespan and fit normative models using GAMLSS, which I won't get into, but it's a generalized additive modeling for location, scale, and shape, which basically means it is that as well as accounting for the change of mean throughout the ages, it also accounts for a change of variance. So basically what that means is at a younger age, there might be a larger spread of certain variables than an older age, when people become more canalized and closer together in some aspects. And applying this concept of growth charts to imaging-derived brain phenotypes has been an idea for a very long time, and this is one of the implementations of it. Sort of showing it at one go, it can show you how these different global phenotypes change throughout the lifespan, but also within each individual, you can track or see where an individual falls against the population. One thing that hasn't been done for these growth charts for age-related changes is taking into account potential effects of gestational age of birth. And this is an interesting question because there is a lot of papers that have looked into whether being born preterm or early has effects on brain development in later years of a child's life. And a lot of papers have found that, yes, there seems to be an effect. And sometimes this effect is focused on specific brain regions more than others, but there's no clear consensus. And then also, it isn't clear whether it changes the trajectory of growth, whether there's like faster growth in some aspects to make up for being born early, or if they sort of lag behind but follow their own percentile. So my project is basically taking this idea of normative modeling for brain imaging phenotypes and modifying the model to include gestational age as a predictor. And I think this is like a very simplified way of conceptualizing it, because it wouldn't just be an intercept shift, it would probably, we would include bend slope as well. But looking at how the trajectories might differ based on gestational age. One way you might think about this is, I haven't shown these, but I haven't shown them for brain, but like you do stratify by sex, for example, because you have different expectations. So one way this could be interesting is whether including someone's gestational age in these predictions can give you a better sense of where they're supposed to fall, given their gestational age. And then, like I said, you can get a score for someone's centile once we have these charts. And then as an endpoint, I'm also interested in looking at how these centile scores are associated with outcomes. And especially whether the charts adapted for gestational age are actually taking away some of the effect association with outcomes, or perhaps they are better suited for looking at how centile scores might be associated with outcomes in a population that was already born preterm. I hope that was as clear as possible, but that's it.
Great. Next, we will have Sarah, who will tell us about physiological mechanisms of cognitive risk for depressive recurrence in daily life. Share screen. There you go.
Right. Hey, I'm a third year PhD student in the clinical science program at the University of Southern California, advised by Dr. Jonathan Stanky, and there's my email. My work that I'm going to talk about today doesn't involve imaging, but imaging is kind of the next step that I'm hoping to bring into the work, because I do have data on this kind of project that I'm talking about. So if anyone's interested in this topic or has any ideas, I'd love to talk more about it. So just like very quick background, I'm interested in depressive recurrence. So we know that depression has a high rate, is a psychiatric disorder with a high rate of recurrence. And one of the key risk factors that I'm interested in is perseverative cognition. So it's been found that people who engage in a high level of perseverative cognition, which I'll define in one moment, have a higher tendency or rate of having a depressive recurrence. So perseverative cognition is commonly thought of as things like rumination or worry, where you're having like really persistent and repetitive activation of negative thoughts, whereas rumination is having repetitive thoughts about the past, and worry is repetitive negative thoughts about the future. Those are kind of classified as PC, or perseverative cognition. And we also know that perseverative cognition prolongs these cognitive representations of stress, along with stress-related affect and physiological activation. And there's work showing that prolonged physiological activation can have negative outcomes, not only in the mental health domain, but also in the physical health domain. And while a lot of the work looking at the relationship between PC, which is what I'm calling perseverative cognition, and depressive recurrence has been at the trait level, there's limited work at what I'm going to call state level, which is looking within individuals over time using intensive longitudinal data. So the data that I am working with here is, or I have worked with so far, is classified as like ambulatory assessment data. So there's like active methods where you collect surveys like several times a day, asking them maybe about perseverative cognition, like in this moment, how much are you worrying, how much are you ruminating, things like that. But then there's also these passive methods like ambulatory psychophysiology, which you can measure with things like these shirts or watches. And then there's some other ones too, but my work is primarily focused on ambulatory psychophys so far. Yeah, this was kind of my master's project. Just like one idea that you can kind of do with this kind of work that I followed up on was, can we use ambulatory psychophys to passively predict moments when people are at increased risk for engaging in PC in daily life? And I looked at this question in people who have never had depression in their life, as well as in people who have a history of major depressive disorder. So I'm not going to go through like the specific results that I found, but if anyone's interested in doing it, this was kind of my master's project. But the idea is we measure several times a day how much they're brooding, how much they're worrying. And then we look at moments when they're kind of perseverating above their own mean, so outside of their normal, and used kind of data from this these biometric smart shirts, which collect heart rate data as well as activity data, to see if we could predict when people were more likely to perseverate, and if there's differences across people who've never been depressed versus people who have depression. And we found some pretty cool stuff. So if anyone wants to talk about it, I'm happy to. And the next step is integrating fMRI data that we have in the sample as well. So yeah.
And I believe I messed up the list. So next up is Elle, who I skipped. Sorry about that. Who will tell us about applying precision imaging methods to understand how sex hormones influence the brain. Sorry about that. Interesting.
I was having internet issues earlier.
Let's see what happens.
I just got a
some
new
security
computer.
setting. Well, we'll do. Let's go to the next one, and then meanwhile,
I can try to
Slack
figure this
your,
out. Okay, I can send my presentation.
okay, we will reconfigure here, and next up will be Ashley. Will tell us, will answer the question: do people neurally represent ambiguous and clearly valent stimuli according to their valence bias? Perhaps.
Okay, and then. Okay. Okay, hi everyone. I'm actually not going to answer that question. I don't have the answer yet. But yeah, so my lab focuses on valence bias. So that is all about how people respond to ambiguous situations. And we can see that people tend to have a negative or positive valence bias. So if they're in an ambiguous situation, and the way that we actually assess this in the lab is have them look at ambiguous stimuli, like faces or scenes, then they tend to rate those ambiguous stimuli as positive or negative. So I can show you, we had people do an MRI task where they were given the valence bias task as a part of like 8 runs, 4 blocks interweaved, and they were given emotional faces or scenes, and they had to rate the valence of them. And you can see a surprise face there. That's what we would say is an ambiguous face, because you don't know if that's surprise because, you know, it's a happy surprise, like a surprise birthday party, or some bad news that they got. So yeah, we scan these people, and valence bias can be represented on a spectrum where you can have the most positive valence bias, which would be a 1, or you can have a most negative valence bias, which would be a 0. And I'm kind of interested in seeing, okay, like we have this data of people in this scanner where they were categorizing themselves as these stimuli as more similar or different, you know. When they say that a surprise face is one, they're saying that it's similar to all the other positive images that they've seen. So are people neurally representing ambiguous and clearly valent stimuli according to their valence bias? So I would expect that people who are saying that ambiguous and positive stimuli are represented, or like people with a positive valence bias are indicating in their brain and also behaviorally that ambiguous and positive stimuli are similar to each other. And same thing for if you had a negative valence bias. And maybe we could see this on a spectrum. So to do this, I have created like prototypical negative valence bias and positive valence bias RDMs, and also a null RDM, which is basically this RDM just shuffled randomly. And I'm going to compare this to an RDM at the voxel level. So this is actually a Searchlight RSA project. But the idea is that if you correlate the model RDMs to the neural RDM that's here at every Searchlight voxel, then how strong is this correlation? And also with the null RDM, I can shuffle it 1,000 times, and every time I shuffle it, I can compare it to every voxel that exists, which is about like 50,000 voxels. So that's a lot of comparisons, but I can generate a null distribution and compare these two model RDMs to this null distribution and see, you know, which model is performing better. And the idea is to finally get some Searchlight maps going, and I can see on a participant level, you know, where are these like stimuli being represented in their brain in a Searchlight, and then also if their valence bias is related to how they're representing these ambiguous or clearly valent stimuli in their head too. Yeah, so that's the idea. I have some, you know, results already. There's some open questions with this. So if you have any, you know, thoughts, just let me know. But yeah, you can find me here. I'm a lab manager at the University of Nebraska-Lincoln, and that's my email. So yeah.
And now with applying precision imaging methods to understand how sex hormones influence the brain. Share my screen. Really?
Hi, everyone. My name is Elle, and I will be talking a little bit today about how I use precision imaging to understand the role of sex hormones in the brain. So I think that a lot of the times people tend to forget that sex hormones such as estrogen, progesterone, and testosterone have a role beyond sort of the reproductive organs, beyond the ovaries or the testes. We might not really consider the brain the seemingly far walled off organ, but of course, these are not separate entities. The nervous and the endocrine system are really tightly linked. The brain, in fact, is one of the most important endocrine organs. And by this, I mean that the brain guides the production of sex hormones from places like the ovaries and the testes, but it's also itself influenced by sex hormones. So areas of the brain that underlie cognition, such as the hippocampus and the prefrontal cortex, are highly packed with sex hormone receptors. And one of the sort of defining features of the endocrine system of hormone production is that it's dynamic. So it's changing at a very high temporal scale. And here we can see sort of a high level overview of sex hormone fluctuations across the lifespan, this blue dotted line being sex hormone production. And this dynamic nature of hormone production, I think, makes it very well suited for a precision imaging framework. And so by precision imaging or sampling, what I mean is basically going very deep on a small number of individuals. So scanning a few individuals or sometimes one individual very, very many times instead of many people 1 or 2 times. And one example of the way that we've done this in the lab is what we call 28Me, a study where we've taken one individual and we scanned her every single day for 30 days straight over the course of complete menstrual cycle, basically to understand how the dynamic production of estrogen and progesterone influence the brain. We then followed up and did this in the same individual, but this time when she was on birth control or OC, this time to understand how chronically suppressing sex hormone production influences the brain. And then finally, I'm really interested into how basically the brain is affected when you sort of disrupt endocrine rhythms. So there are instances such as a surgery or a medication when you either temporarily or permanently reduce or suppress hormone production. And so I'm interested in what happens to the brain when that happens. So what we're doing in this case is scanning individuals before, sometimes during, and then after these events in order to see what might be happening to the brain. And I'm particularly interested in sort of brain morphology as my outcome measure. So I'm always open to sort of learning new pipelines and tools. So if anyone has questions, wants to collaborate or chat, please let me know. Thank you.
And I believe that concludes our lightning talks for today. Thank you so much again to all the speakers. Let's give them another round of applause.